Hello, seniors. Today we're going to continue with the last part of electronic assignment number 7, which is about more rules for derivatives. If you remember, in this electronic assignment, we have seen the derivative of e to the power of x, we have seen the derivative of natural logarithm of x, and we have seen the rules for both the product and quotient of two functions, okay? The rule to differentiate the product or the quotient of two functions. So what I want to do in this video is show you a little bit more examples about how to use the product and quotient rule, and then I'm going to show you different ways to represent the derivative notation, okay, just for you to consider and to understand what each of the symbols imply, okay? So here it says, the product and quotient rules are not needed for all products and quotients. It is sometimes more convenient to rewrite the function before differentiating. So let's see these examples to see what this is referring to. So to make a quick review, this is what we have in the formula booklet basically. The product rule, remember, it's when we have the product of two functions, y equals u times v, and the derivative of y, remember this is the same as saying y prime, is equal to u times v prime plus v times u prime. Okay, and this is another notation for derivatives, but it basically means the same as this. Okay, so this was the product rule, and the quotient rule, if you remember, when we have a function divided by another function, y equals u divided by v, then the derivative of y, or y prime, is equal to v times u prime, the derivative of u with respect to x, minus u times v prime, which is the derivative of v over with respect to x, divided by v squared. So that was the quotient rule. Okay. So let's see how these rules apply to the following exercises. For part A, we have f of x equals root of x times x 4x squared minus 2x. In this case, we could either solve this as a product using product rule, or we could expand this by distributing this root of x and then differentiating it as using a power rule, right? I think that a way is easier for this particular exercise. So we could rewrite this as x to the power of 1/2 times 4 times x squared minus 2x. Okay, and then if we distribute the x to 1/2 to each of the terms, we're going to get the following. We're going to have f of x equals, in the first case, this times this would give us 4x to the power of 2 plus 1/2. Remember, we add the exponents, minus 2 times x to the power of 1 plus 1/2. Right? We're adding the exponents. 1/2. Okay, so if we add this, f of x will be equal to f of x is equal to 4 times x to the power of 2 plus 1/2. That's 3/2, right? To the power of 3/2 minus 2 times x to the power of, this would be, sorry, this is not 3/2, this is 5/2. 5/2, and this is 3/2 to the power of 3/2. Okay, so once we have it written this way, then we can apply the quotient rule, right, which is the first rule we learned to differentiate. So if I find the derivative of this function f prime of x, then this would be equal to 4 times 5 over 2, we take down the exponent and we subtract the exponent by 1. So this is 5/2 minus 1, minus 2 times 3/2 times x to the power of 3/2 minus 1, right? And then if we simplify terms, for example, this term with this term becomes a 2, this becomes a 1, the 2 here simplifies with this 2 over here. So we're going to have that f prime of x is equal to 10 times x to the power of, this would be 3 halves, to the power of 3 halves, minus 3 times x to the power of 1 half, right? And this would be the derivative, okay? We can write this in a more elegant way and say that this is equal to 10 times the square root of x cubed minus 3 times the square root of x. And this would be fine for the answer. Or we could take common factor or whatever, but I'm going to leave it like this. Okay, so that's it for part A. So in this case, we didn't need to apply either product rule or quotient rule, but we're going to see other cases where we will need to apply those rules. Okay, so let's see part B. I'm going to do it here. I'm going to copy a function. It says f of x is equal to 3x plus 4 over x squared minus 2. Okay, so if you see in this case we will have to apply the quotient rule because there's no way we can simplify this in order to apply the power rule or any other rule, right? So we need to treat these functions, this first one in the numerator and this one in the denominator, as different functions and apply the quotient rule, okay? So that's what we're gonna do. So if we apply the quotient rule, we would say that, let me call this ux. I'm going to call it the first function, which is 3x plus 4 in the numerator. So if I find this derivative, u prime of x, this would be equal to 3, right? And then if I find v, or if I consider v of x equal to x squared minus 2, then the derivative of v, in this case, would be equal to 2x, right? 2x. So with this information, I can apply the product rule, the quotient rule, sorry. So I'm going to do that right here. So f prime of x, the derivative of f, is equal to, if we remember the quotient rule, it says v times the derivative of u, so v, the original function, x squared minus 2, times the derivative of u, which is 3, minus, and then we have u times the derivative of v. U is equal to 3x plus 4, and the derivative of v is equal to 2x. And this is being divided by v squared. So that's equal to x squared minus 2 squared. Okay, so once we have this, we need to work the expression in order to get our final result. So this would be equal to 3x squared minus 6 minus 6x squared minus 8x divided by x squared minus 2 squared. Okay, so then we can simplify like terms and we would get as a final result this one with this one. So this would be equal to negative 3x squared minus 8x minus 6 divided by x squared minus 2 squared. And there's nothing else we could do here. No, we cannot apply any factoring case, so this would be the final result. Okay, so this is an example of quotient rule. You see that it's simple, it's easy, it's just applying the formula, right? Quotient rule formula. Okay, so let's see part C. Let me copy the function f of x equals 9 over the cubic root of x to the power of 4. There you go. Okay, so in this example, we could either solve it as using quotient rule, but it will be easier in this case to work it as a power rule. Okay, if we turn this into an exponential fraction and then take it to the numerator, then it would be much easier to work with the power rule. Okay, so this is equal to 9 times x to the power of negative 3/4, right? Remember, the index in the radical is in the numerator and the exponent inside the radical is in the denominator. Okay, so once we have written it that way, we can directly apply the power rule. So we would say that f prime of x, in this case, is equal to 9 times negative 3/4 times x to the power of negative 3/4 minus 1, right? So the derivative of x is equal to, if we can simplify, no, so this would be equal to negative 27 divided by 4 times x to the power of negative 3/4 minus 1, that would be negative 7/4. Sorry, I made a mistake here. I just realized I confused these terms. It should actually be 4. Sorry, I told you the other way around. This should be to the power of 4/3. Yes, because the square root of x, remember, it's x to the power of 1/2. So the index is in the denominator and the exponent is in the numerator. Sorry for the confusion there. Okay, so this should be 4/3 minus 1. So this would be equal to negative 7/3. Negative 7/3. Okay, so if we want to rewrite this in a more elegant way, we could say that the derivative of f, the function f, is equal to negative 27 over 4 times the cubic root of x to the power of 7. Okay, and this would be the final result. Okay, so in this case, there was no need to apply quotient rule, although you could apply quotient rule and the result would actually be the same. Let me show you that just for you to see that it's actually the same thing. So I'm going to do that right here. I'm going to find the same derivative, but applying the quotient rule. So if I call u of x, that's the function in the numerator, it's 9. So u prime of x in this case would be 0, right? And if I call vx to whatever I have in the denominator, then this would be the cubic root of x to the power of 4, which is the same as x to the power of 4/3. So v prime of x is equal to 4/3 times x to the power of 1/3. 4/3 minus 1, yes, that's 1/3. Okay, so let's see if this works if we apply the formula. The formula says that f prime of x, using the quotient rule, is equal to, remember, v times u prime minus u times v prime over v squared. So let's see, this would be v is equal to x to the power of 4/3 times u prime, which is 0, minus u, which is 9, times v prime, which is 4/3, times x to the 1/3. And this is being divided by v squared. So that would be x to the power of 4/3. And this is squared. Okay, so we're going to need to apply properties of exponents there. So f prime of x, if we organize this, would be equal to, all of this term is 0, right? Because we're multiplying by 0. So this is 0. So we're going to get negative 9 times 4/3, that's negative, there's something wrong here, I think. Yes, I forgot to change this order here. Sorry. It should be negative 4/3. There you go. So this is negative 36 over 3 and we are able to simplify that. Negative 36 over 3, that's 12, right? So this is negative 12 over the cubic root. There you go, that's fine. Okay, so now we can go back here and we're gonna have the same situation, right? 9 times 4, that's 36, divided by 3, that's negative 12. Negative 12, x to the power of 1/3 divided by, and this would be x to the power of 8/3, right? So you see, we can simplify this term, this with this, and we're gonna have, instead of 8/3, we need to this decrease it by 1 because we had a 1 here, so this becomes 7 right here, right? So you see that we're actually getting the same result. F prime of x is equal to negative 12 over the cubic root of x to the power of 7. So you see that we get exactly the same result by applying the quotient rule, okay? So that was just to show you that this works, okay? But you see that it's much easier if you could work directly with the power rule, right? Finally, we're going to see exercise D, which is this one. It says, let me write that here, f of x equals 3x squared plus 2x plus 1 divided by x squared. Okay, in this particular case, it is much easier if I avoid using the quotient rule and rather separate this division, separating the terms in this division, right? It will be this plus this plus this, plus this, okay? So if I rewrite this function, this would be equal to f of x equals 3x squared over x squared plus 2x over x squared plus 1 over x squared. And if I simplify terms here, you would see that we can differentiate this much easier, right? This one goes with this, and for the last term we're gonna have, so if we rewrite this, this is 3 plus 2 times x to the power of negative 1 if I take it to the numerator, and finally plus 1 times x to the negative 2 if we take the x to the numerator. So now if we apply the power rule, this would be equal to derivative of 3, that's 0, minus 2, because it's 2 times negative 1, so minus 2 x to the power of negative 2, and then minus 2 again, 1 times negative 2 is negative 2, so times x to the power of negative 3, and that will be it. So here we have our derivative of f, which if we rewrite this more elegantly, we will get f prime of x equals negative 2 over x squared minus 2 over x cubed. Okay, and this would be the result of this gradient function. So you see that in this case, it was much better to separate the terms and use the power rule instead of applying the quotient rule. Okay, so you need to be able to see when it is convenient to work the expression before differentiating or directly applying either the product or the quotient rule. Okay, so we're gonna finish by doing this set of exercises. This just shows different ways in which we can express the derivative of a function, but you'll see that all of the symbols represent the same thing, which is derivative basically. So it says, we have been using the prime notation f prime of x to denote derivatives. We can use Leibniz notation, which is a derivative of y with respect to x, or also this way, derivative of the function f of x with respect to x. And we can also use variables other than x and y. The notation dy over dx is read as the derivative of y with respect to x, or dy by dx, or simply dy dx. The notation df of x over dx is read as the derivative of f with respect to x. But what you should know is that all of these different symbols that you see here represent the same thing, and it's basically finding the derivative of the function, okay? There are different ways of expressing this only. Okay, so let's do these examples. For part A, it says find the derivative of this function with respect to x. So basically what we want to do is find the derivative of the function, okay? So if we could write it, if you want to make it easier, you could write it as f of x is equal to natural logarithm of x times 7x minus 2. This is a function, right, which we want to differentiate. So in this particular situation, we need to apply the product rule, right? We cannot separate, or we cannot simplify this expression to apply a power rule, so we need to apply here the product rule. Remember, the product rule said that f prime of x is equal to u times v prime plus v times u prime, okay? That's what the product rule says. So if we apply the product rule, we're going to have that. I can do this directly mentally. It's u times v prime, so we copy u as it is, natural logarithm of x, times v prime, the derivative of v, in this case is 7, right? Plus v, the original, which is 7x minus 2, times u prime, which is the derivative of natural logarithm of x, that, if you remember, is equal to 1 over x, the derivative of natural logarithm of x. So if we simplify this, we're going to get our final result. Sorry, I'm going to use the notation that the exercise gives. I'm going to write this as the derivative of, the derivative of the function with respect to x of this function, natural logarithm of x times 7x minus 2 is equal to natural logarithm. I'm going to copy a 7 in front. It's equal to 7 times natural logarithm of x plus 7x minus 2 divided by x. So this would be the derivative of the function. I don't like this notation much because it's very long, but you should see it because some IB exercises represent it this way in order to confuse students. But you should notice that it's actually the same thing. Okay, part B. If s of t is equal to 4t squared minus 1 squared, find the derivative of s with respect to t. So basically we're doing the same thing. We're just changing the letters here. So let me copy the function. S of t instead of f of x is equal to 4t squared minus 1 squared. So if I want to find the derivative of this, maybe in this particular exercise, it's better if I expand this before actually doing the derivative, right? So we could say that s of t before doing the derivative is 4t squared minus 1 times 4t squared minus 1, right? And then we're going to multiply this. We're going to do a FOIL method. So we're going to get 16t to the 4th power minus 4t squared minus 4t squared plus 1. So s of t is equal to 16t to the 4th power minus 8t squared plus 1. So now we can differentiate this much more easily. I'm going to use this notation. So ds, the derivative of s with respect to t, is equal to 16 times 4, that's 64, right? 64t cubed minus 16t plus 0, right? So this is the derivative of s with respect to t. Okay, finally, for part C, it says, if a equals pi r squared, find the derivative of a with respect to r, and then here you have an r equals 3, right? this is saying that I later need to evaluate the derivative for r equals 3. So first of all, what I'm going to do is find the derivative, okay? And then we're going to evaluate it for this particular value of r, okay? So first of all, I'm going to copy a function. Function A is equal to pi r squared. So the derivative of function A with respect to r, which is what we're asked, is equal to, we follow the power rule, right? 2 pi r. Okay, so that's the derivative. But then I want to evaluate this derivative, the derivative of A with respect to r, for a particular value of r, which is r equals 3. Okay, so basically what I'm going to do there is replace the value of r with 3. So this is equal to 2 pi times 3. So finally, we're going to get as a result 6 pi. 6 pi. Okay. Before we finish with this class, I want to show you how you can find the derivative of a function using your calculators. Okay, so if you see the calculator right now, we're going to go to menu 1, and I'm going to show you, let me erase this, how to find the derivative of a function using the calculator, okay? So for a specific value. So we're going to use the same example in which the area, the given function was area equals pi r squared, right? So if we want to evaluate the derivative of that function for r equals 3, which is what we had in that particular exercise, we're going to go to math right here, F4, and then here you have the derivative of the function, right? So we're going to click on F4, and you see that derivative of, and here we're going to plug in the function, which in this case is pi, shift pi r squared. We can call this x. We should use x squared because we're talking about the variable x right here, right? So we want to evaluate this function for x equals 3 according to the exercise, right? The value of r. So if you click on execute, you're going to get as a result 6 pi, which is exactly what we got in the electronic assignment. Okay, so that's how you use your calculator to find the derivative of a function for a specific value, okay? So that'll be it, seniors, for this class. I hope this was clear enough for you. If not, please let me know, and have a nice day. See you.